transfer is a phenomenon that arises in many daily tasks and industrial settings. Therefore, it is important to comprehend the dynamic of hot water cooling. This situation is similar to our case study where we have to determine the effect of three parameters, which are the surrounding temperature, agitation duration, and surface area of container to the final temperature of 350 ml of hot water with the initial temperature of 100 degrees Celsius that have been let cool down in a plastic container in just 5 minutes.
Now, let's look at the methodology. This study case used Box-Beacon method to collect the data. A Box-Beacon design is test array specially designed for response surface methodology. In the Box-Beacon design, the levels of the factor are at the midpoint of the edge, red dots, and in the center and the center point, blue dot. This array is often used in RSM to construct a response surface. For each factor are three levels required. The methodology encompasses two main factors denoted as A and B, each with specific minimum and value and maximum values. Factor A relates to the surface area measured in square centimeter, ranging from a minimum of 4.91 square centimeter to a maximum of 14314 square centimeter. Factor B involves the initial temperature in degrees Celsius with a minimum value of 7 degrees Celsius and a maximum 29 degrees Celsius. Additionally, Factor C represents the duration of stirring in seconds, ranging from 7 seconds to 60 seconds. Table 1 and 2 display the data obtained from Box-Beacon. Table 1 displays the dataset for final temperature within block 1 to block 17. Meanwhile, Table 2 displays the dataset after eliminating the outlier. We can see the outlier in Table 2 in the 7th column in the second row. Since the data will cause problem with the model, it was removed.
On this table, we are highlight the maximum and minimum temperature. The maximum is 29.9 degrees Celsius. The minimum is 7 degrees Celsius. When the final temperatures of 350 ml hot water in the different surface area container and surrounding temperatures with duration of stirrings, but same in initial temperature, it is desirable to have the predicted and actual result align closely. With the predicted and actual value for this experiment aligned, it signifies adherence to quality control, efficiency in the process, and one's satisfactions. The model significance is evidenced in the 3302.53 f-value, indicating a 0.1% change to a significance f-value. Factor A and factor B significantly influence the final temperature response. Well, factor C has a non-significant influence. The lack of the fixed test validates the model's accuracy. The mean square of residual is the modulus, indicating the model account for the significant percentage of data variabilities. The anomaly findings that emphasize the importance of factor A and B. The final temperatures model lack of fit test shows a non-significant F-value of 1.86, indicating a well-fitting model. Key mixtures like low standard deviations, high R-squared value, and means of 17.43 support the model's reliability. Adjusted the predictive R-squared value show the reasonable agreements, and the index precision radius of 154.671 exists the acceptable that shows indicating a strong signal to noise radius, indicating the model's ineffectiveness. Figure 1 and Figure 2 show diagnostic graph of the models indicating ambient predictions across independent parameters like plastic container surface area, temperatures, and agitation durations. Figure 2 shows a strong correlations between the model's predictions and actual results, indicating accuracies and helping detect outliers. Both plots help in assessing the model's effectiveness.
The data coefficients provide crucial information on factors influencing final temperature. The intercept represents baseline temperature with a coefficient of 0.28, 11.09, and 0.084, indicating their impact. tight confidence range, and low standard errors indicate preacher's estimates with VIF levels near 1, minimizing component influence. This aids its understanding and using the model effectively. For mathematical model equation based on these variables in Figure 1, the estimated end temperature is calculated by adding the surface area, temperature, and steering duration to 18.12 degrees Celsius. Figure 2 shows a simple equation for calculating final temperature involving real elements like surface area, temperature, and steering periods, which can be easily modified by multiples of these components.
This statistic shows the model projection on the final temperature of the hot water. However, based on the performance, case 10 is potentially an outlier. Therefore, case 10 must be eliminated or refinement must be done to the model. This figure shows the display of a perturbation plot illustrating the relationship between parameters affecting the final temperature of hot water. For factors A and factor C, they have a constant trend for which they do not really affect the final temperature of hot water, while for factor B, it shows an increasing trend suggesting that the factors need to be lower to get the lowest final temperature. This experiment aimed to get lowest final temperature of hot water after 5 minutes of cooling. Thus, this RSM graph shows that the lowest final temperature could be gained when higher surface area of container with highest agitation duration and the lowest surrounding temperature is used when the experiment is done.
Optimization comes next. So this figure shows the parameter setup to get the best testability. The optimization produced aims to achieve the lowest end temperature and maximum efficiency for cooling 350 ml of hot water. The combination of the plastic container with the surface area of 140.14 cubic, surrounding temperature of 7 degrees Celsius, and steering duration resulted in a minimum final temperature of 350 ml hot water. This figure shows the solution based on desirability. It shows the model suggested a desirable solution to get the lowest final temperature of 350 ml hot water after cooling. The optimal solution for the problem is solution 1, which has a desirability of 0.996 with a plastic container surface area of 143.14 cubic, a cooling temperature of 7 degrees Celsius, and a steering duration of 60 seconds. This figure shows the RSM plot based on desirability. The figure demonstrates the correlation between the surface area of the plastic container and the surrounding temperature, with the prediction of 1.00 indicating that lowering the surrounding temperature against the container large surface area lead to the lower final temperature, with a surface area of 140.14 cubic, resulting in the highest desirability.
In conclusion, the investigation on the parameters affecting the final temperature of a 3015 ml of hot water cooling down in 5 minutes under different surrounding temperatures, steering times, and container surface areas has provided valuable insight into the heat transfer and cooling processes of water. The result of the investigation can be utilized in various fields, including scientific research, industrial practice, education, and environmental conservation. The study highlights the importance of understanding the factors that influence the final temperature of water during the cooling process, such as specific heat capacity, heat transfer, and temperature control. The findings can be applied to optimize cooling system, improve energy efficiency, and promote responsible use of water resources.